Hello everybody, this is the second section of Combinational Logic Design in Digital Systems class. In today's class we'll continue discussing more about the combinational circuit design strategies. So there are a few important design approaches when we design combinational circuits. In fact, those approaches are applicable to all types of designs, but here we will be given examples in terms of combinational circuits. A hierarchical design is to keep the complexity under control. This design approach divides the problem into smaller pieces called blocks to reduce the complexity of an implementation. Such an approach has the additional advantage that small blocks, also named primitive blocks, can be used over and over again by different modules later in the design. Hierarchical design starts with the high-level specification and ends up with decomposed blocks and independent design of each block. In other words, hierarchical design is a top-down approach. A top-down design starts with a high-level specification and ends up with a more detailed design by decomposition and successive refinements. There are also other design approaches, like bottom-up design methodology, which start with small blocks and combines them into a larger and more complex functional blocks. Most of our class discussions and the presented material in our previous class videos follow the top-down design approach. One of the popular combinational circuits is the encoder-decoding pair. In a nutshell, an encoder converts a string of bits containing exactly one bit with logical 1 to a binary code corresponding to the bit position with binary logical 1. For example, let us use 4-bit output and let D4 bit 1 and the rest of these are all 0. The output in this case would be 0, 1, 0, 0. Corresponding to bit locations A0, A1, A2, A3, where A3 is the most significant bit, respectively, and A0, of course, being the least significant bit position. Essentially, what input represents is a decimal number 4. The output is transport representation of that decimal value in binary domain. The output could be actual binary representation, a binary coded decimal code, or an ASCII code. It is quite typical to use actual binary representation when we talk about encoders. The decoder, on the other hand, reverses the encoding operation, and we'll talk more about it and its operation later. Let us run through a classical encoding operation that converts decimal numbers to the corresponding BCD or binary coded decimal representations. Since there are 10 decimal digits, the converter has 10 inputs that are named from D0 to D9. The output contains 4-bit BCD code for each digit. If the number I is pressed by the user, the corresponding BCD code is pushed out by the encoder. What you're seeing in this slide is the truth table that corresponds to the BCD code of the decoder. The truth table for the encoder can easily be derived, and that's what you see, where each input bit string has one and only one value being logical 1. The outputs, on the other hand, A3, A2, A1, and A0, constitute the BCD code words. We can write the Boolean expression easily for each one of the outputs as follows. A0 has 1 in the corresponding positions of D1, D3, D5, D7, and D9. That's why we OR all of them. And A1, on the other hand, has 1s in the corresponding positions of D2, D3, D6, and D7. That's why we OR all of them. And A2 has corresponding bit positions D4, D5, D6, and D7, and A3 is equal to D8 plus D9. One thing you would notice is that not all the input combinations are covered, and thus if the input bit string contains more than 1, the encoder will not work. A good design should compensate for all possible input combinations. So let us consider a simpler case where we use 4-bit inputs and 2-bit outputs. On the left, you can see all the possible 4-bit combinations, and the arrows are used to show the mapping to the set of valid inputs. In this case, the valid inputs, of course, are 0001, 0010, 0100, 1000, and all these valid inputs basically corresponds to binary representation of 0, 1, 2, and 3 in decimal. This mapping is derived using the priority of bits. Thus, for example, the bit combination 0011 corresponds to 0010 because the most significant bit position is the second most significant bit position. The priority could have been defined from the least significant to the most significant bit position as well. That's an alternative way. So it's a matter of convention in this case. That change would change the mapping shown in this slide. So that's actually left an exercise that you could have the priority defined from least significant to most significant, and that's your job to do the mapping again, all over again, based on 4 input 2 output encoding example. Next, we show the truth table that includes all the mean terms where x's in the truth table are don't cares. They could be 0 or 1. The V literal holds the validity bit that turns 1 if at least one logical 1 is present in the input. Otherwise, it turns 0. So we can figure out the Boolean expressions for A1 and A0. These are 2 outputs. And the validity literal V as shown in this table. In this case, the Boolean expressions will turn out to be A1 corresponding to D3 plus D2. And in SOP form, and that's also left an exercise to show that using distribution law as a hint. And A0 corresponds to D3 plus D3 dot to D2 dot D1 in SOP form, and you can use one of the postulates and theorems we covered in our previous cases in classes to derive D3 plus D2 prime in parentheses and D3 plus D1 in parentheses. And finally, V is given by D3 plus D2 plus D1 plus D0 in POS form. And that you can basically use the fact that A1 being equal to D3 plus D2, and you can rewrite V as A1 plus D1 plus D0. Here are the set of manipulations to put the Boolean expressions in a suitable form for NAND implementation. And we end up using 4 NAND and 5 NOT gates. It's left as an exercise to verify the correctness of this logic circuit. Decoding is the inverse operation of encoding operation. Encoding produces a coded version of the input, and that code word must be decoded for intelligibility. Here we show a 2 to 4 line decoder where the binary representation of decimal digits 0 to 3 are given as inputs, and the decoder chooses one of the outputs to with logical 1. Left bottom shows the corresponding logic expressions for each output D sub I, and on the right, logic diagram is shown for the decoder. If you expand the decoder to implement a larger decoder, you will notice that multiple input AND gates would be needed, which might not be very feasible. A hierarchical approach is what is usually feasible. And next slide we'll see an example of such a hierarchical design. But before that, I would like to just bring to your attention that we are using 4 AND gates and 2 NOT gates to implement a decoder. But usually decoders are in more compact form when you go and buy one from the market. Let's design a 4 to 16 line decoder using 2 to 4 line decoders. That's a hierarchical design exercise. In this case, inputs A1 and A0 and A3, A2 are use different 2 to 4 line decoders, and all combinations of the outputs of the 2 to 4 line decoders produce 16 outputs named as D0 to D15, representing the decoding result. Including the 2 to 4 line decoders, what's the total number of AND gates used in this hierarchical design, for example? Let's just think about it and compare the cost of the hierarchical design and the cost of the conventional design in terms of the number of AND and NOT gates we use. So one of the interesting questions is, how do we really break a bigger decoder circuit into smaller and readily available decoders to utilize the hierarchical design approach? And here is how we do it. The K to 2 to the K hierarchical decoder design proceeds as follows. We need 2 to the K output AND gates, for sure. If K is divisible by 2, then let the quotient be Q, then use 2 Q to the Q decoders. If K is not divisible by 2, then K plus 1 over 2 is, and k minus 1 over 2 must be divisible by 2, and let the quotients be q1 and q2 respectively for these two cases. Use one q1 to 2 to the q1 and one q2 to 2 to the q2 decoders. Previous example is for k equal 4, and we use 2 to 4 line decoders. An example is the following. Let's design a 5 to 128 line decoder using a hierarchical design technique, and that's left as an exercise. In logic circuits, a designer who implements a function or a module usually puts an extra input port to that so that he can enable or disable the functionality of the logic circuit. This way, an external user of the module can switch on and off the functionality depending on the need and attraction for it. Here is an example of 3 to 8 decoder with an enable input. The truth table clearly manifests the additional row on top that shows the output when the circuit is disabled. Additional enable functionality adds extra 4 AND gates to the circuit due to the AND gate's inherent enable functionality. So here's the example. We've got inputs A0, A1 and an enable port that is basically at the end of the circuit puts extra 4 AND gates to the output, and the output of the circuit is the output of the last stage of the set of AND gates. For any variable x, we have en, the enable input, and that with x gives you x. If en is 1 and it gives 0 otherwise. In other words, en when en is 0. If we switch the port entries and make enable input as data input and A0, A1 to be the select inputs, then the circuit will behave just like a switch, distributing the value of en, the enable input, to one of the outputs D0, D1, D2, or D3. This special circuit is known as demultiplexer, or DMUX in short. We'll see more about this particular type of circuit later in our course. So let's just have an example. Implementation using decoders. For example, we would like to implement a function f. And here is our example, shows an f that is given by a bc prime plus b prime c in parentheses plus abc. If we write this function in SOP form, you'll immediately realize that the decoder outputs and pushes out the minterms. And the last 3 minterms is what we're interested in for this function, and it will, when you OR them, all of them will give us the function f. So that's why the decoder outputs indexed by 0, 1, 1, 0, and 1, 1, when you OR all of them, you will get the function f. And here the a is going to be our enable input, because a is present in all of the minterms of the function f. We also implement the same functionality by taking the function expression's inverse twice. When you do that, from the calculation, we end up with an f is given by a b prime c prime in parentheses, and the whole parentheses is inverted. This means if we set a as the enable input and bc to be the data input, we get the correct functionality if we use the drawn logical diagram like that shown in that slide. And note that NOT gate connected at one of the outputs. In this case, we basically have implemented function f using less number of gates, and still we used a single decoder. And that looks a more efficient design. And finally, we will touch upon the particular functionality called multiplexers. Multiplexers is a combinational circuit, apparently, and output depends solely on the input bits. There is no memory in it. Select bits are acting like location or address information and used to identify the input that passes through the circuit and becomes equal to the output. So k must be greater than or equal to log m in base 2. Otherwise, we wouldn't be able to find enough number of bits to represent each one of the outputs. They are the inverse of DMUX separation. Multiplexers have m inputs and 1 output. there are k control bits for making the selection. For example, if all SKs are 0, in other words, the all select lines are logical 0, then I0 would be selected and transferred to the integrated circuit output. One of the important use cases of multiplexers is the implementation of conditional statements. And here is an example. Let us have 5 variables, a, b, x, y, z. And if a is 1, we are given by, the functionality is defined by the function f1, and that's given x prime y plus xy prime. Else, if a is not 1, then we check the b. If b is 1, the functionality is defined by the function f2, and else, in other words, if b is not 1 equals 0, then the whole functionality of the circuit is given or defined by f3. So let us just use both a decoder and a multiplexer to implement this conditional statement. And that's how we implement it. After determining the Boolean expressions for each of the function output entry, f1, f2, and f3, we can draw the corresponding logic diagrams for each. And here is how the logic diagram looks like. In a nutshell, a quick look at the circuit reveals that the decoder produces all the minterms, and using OR and NOT case, we are able to implement appropriate set of minterms. By taking appropriate set of minterms, we're implementing these 3 functions. And finally, the multiplexer selects the intended function as the output based on the values of select inputs A and B. So there are 3 stages of our implementation of a conditional statement using a decoder and a multiplexer and a bunch of gates. So in summary, in this class we covered design approaches and show how to design few popular combinational circuits. We've shown how to use our background information to deal with combinational circuit design framework, particularly when we have don't cares in our truth tables. After establishing necessary background and reviewing the available tools, in the next lecture, we'll be focusing on the design implementation details of more arithmetic operations, comparators, for example, additions, multiplications, and other arithmetic operations that are very common to digital system design. Please feel free to drop any questions you might have about today's lecture into my email box, and I'll be more than happy to respond to your questions, and thank you very much.